Welcome to CITSA.com.
Planck's quantum theory. Electromagnetic theory of radiations was given by the Maxwell, and this theory regarded the radiant energy as a continuous flow of energy. Maxwell's electromagnetic wave theory successfully explained many properties of the light, like reflection, refraction, diffraction, and the interference. However, it failed to explain the phenomena like photoelectric effect, black body radiation, and the line spectra of the elements. So in order to explain the photoelectric effect, black body radiations, and other phenomena, Max Planck in 1901 presented a new theory called as Planck's quantum theory. According to the Planck's quantum theory of radiation, a body that emits radiation, suppose this is a source of the radiation, it emits the radiations. According to the Planck's quantum theory, a hot body emits radiant energy, not continuously as it was proposed by the Maxwell, rather it emits radiations discontinuously in the form of small packets or the bundles of the energy, and the one bundle of energy is called as a quantum. So according to the Planck's quantum theory, any source of energy that emits the radiations not continuously but discontinuously in the small packets of the energy, the bundles of the energy, and one bundle of energy is called as a quantum. So quantum is one packet of energy. The energy associated with one quantum of this radiation is directly proportional to the frequency. So we can say energy associated with this quantum, the energy associated with this particular quantum is directly proportional to the frequency of the radiation. Or you can say the energy of this one quantum will be equal to h nu, where h is a Planck's constant, which is equal to 6.626 times 10 to the power negative 34 joule second. This is the unit for the Planck's constant. So that means energy of the one quantum is equal to h nu, Planck's constant times its frequency. And we know velocity of the light, which is equal to this frequency into wavelength. So you can also write it like this: frequency of the light will be equal to velocity of the light upon the wavelength. And if I put this value over here in this equation number first, so what shall I get? We can have energy of one quantum will be equal to h c by lambda. So here h is constant, velocity of the light is constant, the velocity of the light, which is c is equal to 3 into 10 to the power 8 meters per second. This is the velocity of the light. So that means here we can get one more conclusion: energy of the one quantum is inversely proportional to this wavelength. So higher wavelength means lower energy, and here energy is directly proportional to the frequency. More frequency, higher frequency means high energy. The total energy emitted by a body will be equal to the total energy emitted by the body will be equal to n times energy of the one quantum, which is h nu, and here n is, you can say this is the number of the quantums, right? The number of the quantas emitted or absorbed by the body. So when a particular source is emitting, for example, if you have a source and it emits n number of the quantas, the total energy emitted by this body will be equal to n times the energy of the one quantum. The quantum of the the light is called as photon. So photon is actually a quantum, but it is, you can say photon is a quantum of light. quantum of light. So you can say every photon is a quantum, but every quantum cannot be called as a photon. Photon is a specific name for the quantum of the light. Now let's calculate the energy of the one quantum of the radiation that has a frequency of this much. As we know, energy of the one quantum is equal to h nu. So h is a Planck's constant, which is equal to 6.626 times 10 to the power negative 34 times the frequency here is 6.25 times 10 to the power 14 here. So therefore energy of this one quantum here will be equal to 6.626 times 6.25, so it comes out to be 41.41 times 10 to the power negative 20, or I can say it is equal to 4.141 times 10 to the power negative 19 joules. This is the energy of the one quantum. And what will be the energy for 1 mole of quanta? Now let's calculate for the 1 mole. For 1 mole it will be the energy of the one quantum, that will be equal to 6.022 times 10 to the power 23. This is the 1 mole of particles, 1 mole of photons, or you can say 1 mole of quanta, times the energy of the one quantum, which is 4.141 times 10 to the power minus 19. So which will be equal to, it will be 24 times 10 to the power 4. Okay, 10 to the power 4. So which is equal to 2.4 times 10 to the power 5 joule. This is the energy of the 1 mole of the quanta that has a frequency about 6.25 times 10 to the power 14 hertz. Hope you got the concept. Thanks for watching the video. Bye for now.